Okay. 2 more minutes. Yeah, we're gonna really start at 1:45. Yeah, okay. Okay, welcome back for those who want to watch the second part of the on lecture 5. I do expect a little less audience now because there's no in-class quiz, and you can always watch the recording at a later time. Okay, I promised to do an example, and we're going to do the example of a load swing, right? Or you could also say it's a pendulum on a moving base. Okay, and how does it go? What is the problem? So we have some moving base right here. No, other way around. Moving base here. And then we have some pendulum thing, or some rigid body thing. And let's draw a line here to the CM. So here's the center of mass of the body. This has a length L. With the vertical, it makes an angle alpha. It's the vertical. And then there's a distance S from the wall, from the origin. So we need a coordinate system, so that's X and that's Y. That's the coordinate system, and orientation phi is like this. Then I already have introduced these two generalized coordinates. Let me check if everything is running. Yeah, looks good. Everything is running here too. Yeah. We have gravity, of course, downward. So then the CM coordinates are, well, we only have one body, so that's X, Y, and phi of this body. X, Y, phi. And then for generalized coordinates, yeah, I choose to take this S, this distance S from the wall, from the origin, and this angle alpha from the pendulum. So 2. Why does it have 2 degrees of freedom? Well, the body in itself, of course, has 3 degrees of freedom, and there's only one constraint. This point, the inch point, cannot move up and down. Well, as we said, you also have generalized forces, and in this case it should be a force. This is S is a distance, so this should be a force Fs, and this should be like an M alpha. And in this case, they're easy to identify. The Fs is like an action-reaction force like this, Fs, on this attachment point. And the M alpha is a torque action-reaction, M alpha on the body, and then a reaction on the base. And maybe I extend the base a little bit, so there's a reaction torque here, M alpha, with respect to the base or the inertial world. Okay, for this example we're going to look how does it work with the TMT method. So TMT method, how does that go? Well, as defined in the first lecture, we have to start with a coordinate transformation, right? So we have to, we start with the expression of CM coordinates in generalized coordinates. Or in other words, we have to write down xi is some ti of qj. That's just kinematics, and then we have to look at our picture, right? So we get the coordinate, x coordinate of this body. What is it? Well, the distance s, and then this horizontal distance. So first this distance and this. So it's the s plus, then we have L here, and it's sine alpha. Then the y coordinate, well, that's apparently down, so that's minus L cosine alpha. And the angle phi of the body, well, you could say, well, if the body is horizontal, it would be 0, so, and it has the same direction as phi, so it could be alpha minus pi over 2. I mean, it's irrespective of what this constant is, but just to show that initially you start here and now it's like here. Okay, with this we just have to form our equations of motion, and let's remember what they are. So we had a mass matrix MIK, which was transformed like with a TI. What did I use for indices? I don't remember. TIJ and KL, yeah. TIJ, TKL. I mean, it doesn't matter what the dead indices are, but I like to repeat the same as in the notes before. Q double dot L, because this is this multiplication, is on the right hand side. Well, what should be the outcome? The index, well, the K is there, the L disappears, the I disappears, so the only one is a J, so there should be a J on this side too, QJ, plus, and then we get a TI, yeah, TI, comma J, right? And then we get our forces, our applied forces, and then we have our mass matrix MI, and it can be, there can be a K, it's a dead index, that's an HK, that's okay. Now, do we have all the ingredients? We have this mapping, and then we have to differentiate that again, so that works. We need a mass matrix, so in our case, what is the mass matrix? So the MIK is a diagonal matrix, and it's just a mass, and an inertia. Or in other words, you can also write it out, M, and I, and these are all zeros. Then the next step is, of course, these Jacobians. I mean, these are identical, only one is a transpose of the other one. So the Ti, comma J, what is it? Well, we first have to differentiate then with respect to our generalized coordinate S. It's a matrix of 3 by 2. So first with respect to S, that's a 1. And then the x coordinate with respect to alpha. So the sine, that's becoming a cosine, so we get L cosine alpha. Then the second row is the y, differentiated first with respect to S, there is no S. And then cosine alpha with respect to alpha, that's a minus, so a double minus becomes a plus, sine L sine alpha. And then lastly this one with respect to S, again 0, and then with respect to alpha, it's a 1. Or in other words, and that's usually easier actually to do, you can say, oh, what is x dot? X dot is S dot, and then I have to look at the equation, yeah, is S dot plus L alpha dot cosine alpha. Y dot is, well, there is no S, so that's L alpha dot sine alpha, and phi dot is equal to alpha dot. And this is sort of easy because then from this you immediately identify, oh yeah, it's 1 times S dot and L cosine alpha dot, 0 S dot L sine alpha alpha dot, 0 S dot and a 1 times alpha dot. That's also a nice way to find this Jacobian, just by differentiating it with respect to time. Okay, then what else do we need? Let's look at the equation. So we have these Jacobians. We have, are there any applied generalized forces? Well, there are not. We're not putting some extra force here, or not putting some extra torque here. There is gravity, so apparently there is an applied force. So our applied force Fi is in the x direction 0, and then minus mg in the y direction, and no torque. That's a general CM type of forces. What else do we need? Well, the last thing, so this guy we now have, that's 0, so we have no applied general forces. No applied generalized forces. And these are the applied CM forces, you could say. No applied. Then we have this mapping, then we have the applied forces, we have the mass mapping. Oh, the HK, that had to do with the accelerations, that was the convective term. Now, yeah, let's just determine what are the accelerations. So x double dot, y double dot, and phi double dot. And in doing this, you see a nice trick. Well, first of all, you have to do no differentiation whatsoever. You only put an extra dot on top of all the dots. So s double dot plus l alpha double dot cosine alpha. Here we get l alpha double dot sine alpha, and here, oh, maybe it's a nice spacing, alpha dot like this. So what am I doing there? Which part of is that? Well, that's actually, if you write x double dot I, that's the ti comma j x double q double dot j. And yeah, clearly that this guy is of course this guy, the Jacobian. So you don't have to think about it, just put double dots there. We're not interested, by the way. This part is not interesting. We already have it. What we want to have is this extra part, this ti lm q dot l and q dot m. And without doing this, you can derive this, because how does that go? Well, then we have to differentiate this with respect to s times s dot. Well, there is nothing, right? So with respect to s times s dot, so you could say that's 0 times s dot, for clarity. And then we have to differentiate it with respect to alpha. There is a term there, there's a cosine alpha times alpha dot. So cosine alpha becomes minus sine alpha, so we get minus l alpha dot squared sine alpha. Yeah? Or even you can, in a more deductive way, it could even better be written like L alpha dot sine alpha times alpha dot, right? Then the next part, well, there is no S, so again you get 0 times S dot. There is an alpha, and then you get plus L alpha dot cosine alpha alpha dot, right? And the last one, there is no S and there is no alpha, so 0 times alpha dot plus 0 times alpha dot. So then these HK, by definition, are now these terms, which then just degenerate to the simple term minus L sine alpha alpha dot squared, yeah. Then plus L cosine alpha alpha dot squared and a 0. And here you see the point I make, these are convective accelerations. And in our case, we will later on we will see these are actually the centrifugal ones. Centrifugal ones. Okay, but that is for later on. Now, actually, we have mapped out everything, and the only thing is just combining everything. We have to make the transformed mass matrix, and we have to make the right hand side. Let's start with the transformed mass matrix. So ti, what did I write? I want to keep the same indices. So this part tij mik, yeah. j m I k t k l, or if you like that, t transpose mt. Yeah, that's also a way to write it. Or like this. So let's take the transformation matrix. So this guy, I have to remember that. That's a 1, an L cosine alpha. That's a 0, that's a L sine alpha. That's a 0 and that's a 1 times the transpose, of course, times the mass matrix, which is MMI, and I forget the zeros now for clarity. And then again this matrix 1L cosine alpha, 0 L sine alpha, 0 1. Then the first step is, of course, you multiply this with this, but that's sort of simple. It means that this gets multiplied with m, this gets multiplied with m, this gets multiplied with I. So in it's a matrix times this vector, and the outcome is this times this is a m, this times this is ml cosine alpha, then a 0 ml sine alpha, and then the last part is of course I. Then we have to multiply this guy, the transpose, with this guy, and if you do that, then finally the answer is, of course, take this row times this. If you have to transpose this, so this row becomes the row becomes this column, so this column times this guy, sort of handy actually, so that's an m. Then this column like this guy, so that's a ml cosine alpha. Then this guy times this, so that's again ml cosine alpha, and I'm happy because I get a symmetric thing. And then the last part, that's an extended one, that's this guy times this guy. So that's m L square cosine square alpha plus m L square sine square alpha plus I. Well, of course, this cosine square plus sine square is 1. So in the end, that comes down to the following matrix. We get an m, we get an ml cosine alpha, we get an ml cosine alpha, and we get an ml squared plus I. So that is our transformed mass matrix. The next step is, of course, on the right hand side, all the forces. So we repeat again this transformation matrix, 1L cosine alpha, 0L sine alpha, and here 0, 0. Transpose times. Well, we had forces here on the right hand side, 0 minus mg 0. Then we had this mass matrix minus this mass matrix mmi, and that is then times our convective accelerations, and this is a minus L sine alpha, alpha dot squared, plus L cosine alpha, alpha dot squared, and a 0. Then we close the bracket, and then of course we have our applied forces Fs and M alpha, but in our case they're 0, but I just put them there for generality, so you know, oh yeah, those are the QJs. Okay, now the rest is just doing a nice multiplication. So we have to flip this again, right? So this the row of this one is this column, so this column times this guy, well that's 0, right? So that's a 0. Then this column times this guy, so that's a minus mgl sine alpha. Yeah. Then the next step is this times this and this, so again there's a minus sign going on there, and then the answer is Well, you just, in your mind, you can multiply this with m, this with m, this with I, so it's only everything multiplied with m, and then with these two columns. So for the first one, so I get minus ml sine alpha, yeah, this guy times this guy with an m, so that's minus ml, what is it, sine alpha dot squared, right? Then the second one is a bit more complex, this guy times this guy. So what do we get? And don't forget the m's. So we get L cosine alpha times ml sine alpha with a minus, that's the first one, alpha dot squared, and then with the plus we get plus L sine alpha ml cosine alpha dot squared, and then plus of course these generalized forces. Now we see that these cancel out, so this term cancels out to that, cosine sine, sine cosine, plus minus, and it looks a little bit like this is the cancelling out we also got in the Lagrange equation, but actually it's not, and I will discuss that at the end when we have all the equations formed together. Okay, so this is again plus qj, right? So now we can combine everything and write down our equation of motion. Equation of motion in terms of our generalized coordinates. What do we get? Well, we have this mass matrix M, and then we have ml cosine alpha, ml cosine alpha, and then we have ml squared plus the mass moment of inertia times s double dot alpha double dot equals, and then on the right hand side we have, for generality I write fs, but that's usually 0. Then here we have a term, this term, and that becomes a plus, so plus ml sine alpha alpha dot squared. And then we have here a m alpha, again for generality, and then we have this goes away, this is the remaining minus mgl sine alpha. And these are the equations of motion of this pendulum in terms of generalized coordinates. Okay. Now let's look in detail what is going on. First of all, you want to check your results, right? That's important. And to check your results, what do? You're gonna look at some dimensions, probably. Are the physical dimensions right? But first of all, is the mass matrix symmetric? Well, yes, it's symmetric, so that is good. It's a symmetric thing. Secondly, the first equation should be a force equation. So mass times acceleration, that's a force. And then here we get mass times length times angular acceleration, that's also a force. This is meter per second squared times kilogram. And then on the right hand side we also have meter, kilogram, meters, and per second squared. So that is a force. So that is okay. I'm happy with that, with the units. Then the second equation is a torque equation. So we get an acceleration times a kilogram. So we get newtons times this length, meters. So Newton meter. That's good. Here we get kilogram meter squared times per second squared. So again we have Newton meters here. And on the right hand side we have newtons. We have an acceleration g times the distance, so again we have Newton meters. So that's good. These are newtons and these are Newton meters. So the dimensions are okay. I didn't forget about a length or an alpha dot squared or something like that. That looks pretty okay. What else can you check? Well, you can try and interpret all these sine and cosine things. Well, the sines and cosine things within here, I will get to that in a second. Let's first look at the applied forces, because normally we're used to mass times acceleration as force, but here we have some strange forces. Well, here we have gravity, which we probably can identify, but here we have like a centrifugal force, but only with a sine alpha. So the big question is, why is that? Well, let's draw our pendulum and let's make a bit more sketchy figure out of it. So we have with the vertical, we have here this blob type of thing, right? Here's the CM. And what is going on? We have coordinates going on. We have an S here, and we have an alpha here. Now, if I would draw the accelerations on the CM as a function of the accelerations of the generalized coordinates, I would draw arrows like this. I would draw for the S double dot, well, forget about all the other motions, only do an S double dot, meaning that the whole thing is then moving in this direction with S double dot. So on the CM I have a S double dot like this. And if I only have an alpha double dot and no S double dot, then I get an alpha double dot times L on this one. And already from this one, looking at the mass matrix, you can say, oh, so apparently this alpha double dot L times the cosine of this angle alpha, because here we also have the angle alpha, and this is also alpha. Apparently in the linear case we also get a contribution of alpha double dot times L, but only when it's in a crooked state the cosine of that. So that sort of exemplifies why we get in this linear case not only an ms double dot but also ml cosine alpha double dot. So that's one way. That's explaining the term m alpha double dot L cosine alpha, which is here in the equation. And the same reasoning you can hold for the second one, but let me stay with this one first. Now the second one, I like to look at all these forces here. So I'm going to draw again my potato-like thing. Yeah, and I put in these coordinates S, and I need the alpha, of course, and I need the CM here. So here's the CM, and here we have our alpha. Now what I'm going to draw in the figure is an angular acceleration, right? So if all the accelerations we have to draw into the figure, I already have drawn here this first part, and now I'm going to draw the second part, these convective terms, and that is an acceleration, yeah, that's in this direction. And that acceleration has the magnitude of alpha dot squared times L. That's an acceleration, right? And that's a convective acceleration, so that's something on the right hand side. And now if we look again into the S and in the alpha direction, we clearly see in the S direction, so this is the S direction, right? S direction. We see a projection of this part in the S direction, and the projection has to do with the sine of alpha. It's only this component, as we can see. And if you think in terms of D'Alembert forces, it's minus. So the D'Alembert idea is minus the mass times some acceleration, and that acceleration is alpha dot squared L. And in this case, we need also a sine alpha, and since it's in the minus direction, it's becoming a plus. So this is an explanation of why do we have this force here. Now in the alpha direction, so this is the alpha not a dot. This is the alpha direction. In the alpha direction, the the centrifugal acceleration has no component. They are perpendicular. And that's exactly what we saw in this cancelling out of the thing. So that cancels out that part. Then we're stuck, of course, with one other force. Let's go back to 100. Oh, 100. Where are you? 100. 100. No. Yeah. Then we have this force for the torques. Well, that is actually super clear. If you look at the picture, you have a mg here, and then if we look into the different directions, so in the direction of s, there is no mg component. They're perpendicular to each other. But in the direction of alpha, we have a component. And what is the component? Well, the alpha is again here, right? And it's again minus mgl times the sine of alpha. That is this component. That's in this. Then I should put. That's in this alpha direction, and it's opposite. Therefore, we have the minus. So these explain and why we get the different terms in the equation. In hindsight, of course, you could also put your whole hand on the equation and say, well, forget it. I'm super smart, and I take this picture and I cook up the equations like that. That could be done, maybe for the simple two-dimensional case here, but if things become a bit more complex, that's undoable, of course. But explaining things help to get the signs right and the components right. Okay, the last 15 minutes I like to spend on one of the quiz questions, and that was remember that one of the quiz questions was that we looked at this moving pendulum, but in our case it was not. It was just a point mass, so it was like this, and then we had a point mass here, just m, and then we had these two coordinates, s and alpha. I think in the quiz they were called a, but let's call them s and alpha here. And then there was a question on I gave the equation of motion, and if I now think, well, the equation of motion are just ml cosine alpha, and then here ml cosine alpha, and the only term I get here is ml squared, because I have no mass moment of inertia. There is no inertia here, so that I squared is gone. And then I have alpha double dot, s double dot, s double dot, and alpha double dot, and then I have some forces on the right hand side, and for now that's not so interesting. The thing is, of course, can you solve these equations? Is there always a solution? And you would say, well, there should be, right? Because this is Newtonian mechanics, so if you say what the angles are and if you say what the angular speeds are, then there should be a unique solution. It's not that Newtonian equations can give double solution, non-unique solutions. However, we made this coordinate transformation, and doing this coordinate transformation, you could have done you could have chosen coordinates which are actually not so smart or not so handy, and then you can end up in some singular configuration. So let's see if that's the case. Well, the only way to find out if there's a unique solution in the case of linear equations, a unique solution in terms of accelerations, then you say, well, the leading matrix, the determinant, should be non-zero. So let's look at the determinant of this leading matrix. So that is m squared L squared minus m squared L squared cosine squared alpha, which we can write as m squared L squared times 1 minus cosine squared alpha. And the question is, can that ever be zero? And the answer is yes, unfortunately. Unfortunately, it can be zero. And how can it be zero? Well, when this cosine squared alpha is 1, or in other words, when cosine alpha is plus or minus 1, or in other words, when alpha is 0 plus or minus k times pi. And that looks a bit strange. So in the case where the angle is 0, so in the vertical case, there is no unique solution. So let's focus again on that. So let's redraw it. So now we have this pendulum, and the S, it's immaterial, and it's in this vertical configuration. So this is alpha is 0, and then there's no unique solution. So what is going on? Well, if this is S, and we had here the angle alpha, then here we can have a speed, S dot. And now let's assume that the speed distribution is like this. Those are the speeds. Or in other words, if you would do like this, the minus alpha dot, minus because alpha was initially like this and now it's the other way around, is, and this was the length L, is S dot over L. And in this case, we have a zero velocity. So we have finite or non-zero generalized velocities, and in this case they are Q dot is in this case, well, S dot, and well, let's take S dot is 1, I just take a number. So this is just 1 and then 1 over L, with S dot is 1. And then it should be a minus here. And then we have for these non-zero generalized velocities, we get a zero velocity of the mass. Or in other terms, we get zero kinetic energy for a finite value of the velocities. And that is of course not possible, because we would expect that with a regular mass matrix, the kinetic energy T, no confusion with the transformation matrix, is 1/2, and we have Q dot J, or I is also okay, Mij with a bar, right, Q dot J, where this is the transformed mass matrix. In our case, this M bar is M, ML, ML and ML squared, in the case for alpha is 0. Then apparently when you put in these speeds for this mass matrix, then the result is that is 0. Now let's look if that really happens. So let's take this mass matrix, so the mass matrix M, ML, ML and then ML squared times this velocity 1 and minus 1 over L, and then we have to pre-multiply with this and put a half in front of it, we get minus. Well, if you do that, it's clear, it's 0, 0, and the whole outcome is 0. And that is the deeper ground. The system is in a singular configuration. Why? Well, because we choose these very strange, well, not so strange, but these generalized coordinates, which can end up in a situation where you have a 0 speed for this thing. Of course, you can solve it by adding some inertia to the thing, or by using other coordinates, and that's also another way to do it. In conclusion, what can we say about this? We could also find this velocity by looking at the eigenvalues and vectors and eigenvectors of this mass matrix. If you do that, then you will see that you get a 0 eigenvalue, and then the corresponding eigenvector is then 1 and minus 1 over L. And that shows that the thing is singular. Okay, that finishes our lecture for today. And because we end up about between 5 and 10 minutes earlier, because there's no real interaction with the audience, unfortunately. Next week we have again this online thing, and then we're going to talk about, what is it, chapter 15, numerical integration of ODEs. Well, I hope this was useful. Please give me feedback. It can be either in the WhatsApp or by email or by phone. You just can call me. Please give me some feedback on the pros and the cons of this. Are things good for you, or should I improve things with this a purely online thing. Also, I'm curious about how the office hours work for you. It's now all done via Skype. Either it can be a Skype address. There's also Google Hangout because you have the Gmail address. As you like it. Okay, good luck with the homework, and I see you next week.